All right, guys, let's look at lesson one, which is kinetic molecular theory, which is going to help us distinguish between ideal gases versus real gases. So let's first talk about entropy. Entropy is disorder or randomness, and entropy will increase when your temperature increases, when something dissolves, or when it becomes aqueous, and it's the highest in gases. Gases have very, very, very high entropy. So when we compare states of matter, when we look at particle arrangement for a solid, a liquid, and a gas, we have solids are close ordered, they vibrate in place, they have high intermolecular attractions, they have a definite shape, a definite volume, and low entropy. For a liquid, they're less ordered, they flow around each other, they have medium intermolecular attractions, they take the shape of their container, they have a definite volume, and they have a medium entropy. Gases are far apart, they have complete disorder and random movement. They have very low intermolecular forces of attraction that hold them next to each other. They take the shape of their container, they fill their container, and they have very high entropy. So gases are most affected by changes in temperature, pressure, and volume because of those things. So when we look at the kinetic molecular theory and we want to compare ideal versus real gases, ideal gases are imaginary. They follow the gas laws. The particles are not attracted to each other. The particles have no volume, so their volume is technically negligible. The particles move in a straight line of motion and they have elastic collisions, which means when these gas particles bounce off one of another, they're elastic. So they crash into each other and then they bounce off. They don't lose energy or anything. Real gases, the actual gas that we work with in lab, they do not follow the gas laws exactly. The particles do attract to each other because there is some intermolecular forces of attraction between them. They do have some volume because they have an atomic radius. They do not necessarily move in straight lines, and they don't have elastic collisions. So gases behave most ideally under conditions of high temperature and low pressure because particles are moving faster and the particles are further apart, which is why they're ideal. That means that they have a less chance of the gas particles being attracted to one another because they're farther apart and they're moving faster. Gases deviate or stray from the ideal conditions when they are at a low temperature and high pressure because the particles are moving slower and the particles are closer together. Why is this true? That's because gas particles will be attracted to one another. So, summary. Ideal gases are perfect gases. They have no mass, no volume, no attractive forces that are going to make the molecules interact with one another. When will real gases behave as ideal gases? When they're spread out, when their temperature is high, and when their pressure is low. So I used to think of that as Plath. So pressure is low, ideal gas, high temperature. So when we talk about gas pressures, okay, that's the force exerted on the container walls by the particles in a gas. And we use kPa, which is kilopascals or ATM, and we have standard temperature and pressure conditions, which we have in your table A in your reference packet. So what affects pressure? The amount of gas, the number of moles of gas. So if you increase the amount of gas that you have, you're going to increase the pressure. If you decrease the amount, you're going to decrease the pressure. Temperature, you increase the pressure, you're going to increase the temperature, and decrease the temperature, you're going to decrease the pressure. If you decrease the volume, you're going to increase your pressure, and if you increase your volume, you're going to decrease your pressure. So, when you're looking at tires in the winter, they deflate because of temperature changes. And that's why you have to add more air to them because of that fact. Let's look at a practice. Under which conditions of temperature and pressure will helium behave most like an ideal gas? I'll give you a hint. Think Plath. Okay, so we need a pressure that is low and a temperature that is high. So pressure low, temperature high. So the answer for this is going to be C. What about this practice? An assumption of kinetic theory of gases is that the particles of gases have little attraction for each other and a significant volume, little attraction for each other and a significant and an insignificant volume, strong attraction for each other and a significant volume, or strong attraction for each other and an insignificant volume. Remember, the assumption of the kinetic molecular theory is that particles that are a gas have a little attraction for each other and an insignificant volume. So the answer for here is B. Let's look at this, check your understanding. Under which conditions of temperature and pressure would a sample of H2 behave most like an ideal gas? We're going to talk about this first thing tomorrow. Have a good night.